Hello and welcome to Network Design for Live Production from IET Media. IET Media is the Institute of Engineering and Technology's technical network for engineers involved in all forms of media. Our presenter today is Gerard Phillips, a systems engineer at Arista, who is an experienced broadcast technologist, previously with Snell, who has spent many years driving innovation with a focus on media and entertainment. Gerard's goal is to help bridge the knowledge gap that exists between the broadcast and IP industries as we make the transition from SDI to IP for live production and playout. So, Gerard, hello and welcome. Over to you.
Hi, today I'd like to talk to you a little bit about network design for live production. I guess I mean network design for live IP production, 2110, AES67, those sorts of technologies that we're seeing moving into the live production workspaces these days. So I'm going to start off with a little bit of context just to make sure that it's not a straight leap into network design. Why are we going to move to IP? Why are we moving to IP? So there's a bunch of things which come with the move to IP, and they're really valuable, and I can see that they're making changes already to the way people are building their workflows and building their live productions. I'm going to run through a few of them. So scale, for example, there aren't a lot of UHD SDI routers out there. There's some, but there's not that many. Move to IP gives you the ability to kind of leverage the scale that the IP world can achieve in a non-blocking line rate throughput IP routing environment. So, for example, quick box on the right hand side there. It's a 7RU box. It can accommodate enough non-blocking bandwidth throughput to accommodate 4K by 4K at 3 gig. So a 4K squared router at 3 gig. There's a lot of power there. Once you move to IP, then actually the transport becomes just plumbing. You know, moving the IP packets around is plumbing. It leaves a lot of space for broadcasters to change the formats, go high frame rate, add bigger resolutions, go from UHD to UHD2. There's lots and lots of flexibility just in the fact that you've decoupled the transport mechanism from the physical infrastructure, like we were a bit tied in with SDI. Lots and lots of physical space, weight and power savings are available. OB trucks, for example, you could save a fair proportion of the weight of the OB truck in the copper that you're not putting into miles and miles of BNCs running around the place. You can see the density that can be achieved in IP, so that turns straight into power, space, and cooling savings. It's not all rosy, but there are a lot of those sorts of kind of environmental benefits. And then the one that's really, I think, most important is changing workflows and changing the way we're creating stuff. Being able to kind of have any flow available to anybody and have anybody working anywhere. These are things that are really changing the way that we're working. Certainly right now with big growth in remote production, distributed production, people working from home, people having to work from home. This sorts of IP connectivity is really making a big difference to the way people are building their workflows and being able to be more agile. The shared resource model, the shared flow model really allows you to create different workflows, but be agile about the way you do it, change the way you do it as you need it. And lastly, we're sat on the top of this kind of technology wave that is the COTS wave of IP and compute. We're still sat on Moore's law. Actually, switching infrastructure is running quicker than Moore's law because we're running to catch up with the silicon geometries that are being used by Intel, for example. We're still, they're down at 7 nanometers, 5 nanometers. We're still building boxes out of silicon made out of 3 or 4 generations ago. So we can catch up with that very quickly. What that gives us is a doubling in the size, footprint, throughput. So 4 times the capacity, essentially, every 12 to 18 months, and still going. I mean, that'll run out at some point, but it's still going now. And that kind of acceleration is being driven by the cloud titans, Google, Facebook, those guys, Amazon, who are looking at 400, they're using 400 gigs now, they're looking at 800 gigs, so it's moving really quickly. I want to very quickly cover why is live production different, why is IP live production different from IP enterprise? That's what I'm trying to get to here. What is it that's special about the way we're using IP when we're talking about live production rather than connecting to a printer or running a cloud data center? It's really about different traffic patterns. The typical traffic patterns in most enterprises, campuses, data centers is unicast, and it's protected typically by TCP IP retries. When we get to live production, we're talking about multicast. We're talking about, we're not talking about unicast. We don't have the protections that TCP can afford unicast traffic. We're building UDP, best effort connectivity using multicast. We've got the fact that multicast is one-to-many. I'll cover that later on, or can be one-to-many. So that really fits our workflows. Extremely high bandwidths, anything from a megabit per second for an audio flow or a compressed flow up to 11 gigabits for a 5994 UHD, and of course up to 40 odd gigabits for a UHD2. Large flow counts, enormous flow counts, tens of thousands in big systems of discrete multicast flows. So in terms of table sizes and the ability for the infrastructure to cope, it's not the same as a campus switch. It's not the same as a enterprise switch. These are completely available off the shelf COTS kits, but it's not just any old switch. And of course, one of the things, massive difference in the traffic pattern in terms of kind of the way that it's presented to the user is full duplex, asynchronous, multi-flows per bearer. So where a coax would give you 3 gigs, 12 gigs across 100 meters or something for a single signal, we're now talking about 100 gigabit per second can get you 10 kilometers. It can do 8 times UHD both ways, so 16 UHD signals. And the newer 400 gigs can cover the same distance if that's what you need, and that can get you 35 times UHD. I mean, so we're now talking about a proper big live production camera setup, 35 cameras, big, down a single fiber pair if that's what you need. So some of those scalings can really help simplify the way we're building stuff. I will cover multicast very briefly. I'm sure most people know what it is, but let me just cover it very briefly. So there are 3 sorts of traffic in an IP system. You've got broadcast, which is a one-to-many model. The traffic goes from one source to every destination in the subnet within the VLAN. So it's locally scoped. Really handy when you don't know who you need to talk to, but you just know somebody's local. So that's broadcast. That's not much use because it's can't get out of the subnet and it goes to everyone. Unicast, that's what most traffic is in a network. It's one-to-one. The source knows where the destination is. The source defines where it's going, where the source, the traffic goes to where the source defines it to go to. But it can be routable, so it can escape from that subnet, from that VLAN. But again, it's one-to-one, so not much use for us. Most cameras will go to the shader, the vision mixer, the multi-viewer, the ISO recorder. So that's 4 already, right? Multicast. This is the one that works for us. It's one-to-many, or many-to-many, many-to-one, many-to-none. It's not, the traffic is not defined by where the source wants it to go to. It's defined by what receivers want to receive it or how the orchestration system wants it to be delivered. So it's very much more flexible. And at being a one-to-many, that particular model fits us very well. One camera goes to many places, but not all the places, and it can be routed. Just a very simple overview of the sources and destinations again. So in this particular case, we have a camera. The camera sends the source into the network. You can see that we've got 2 places that want that. They do a traditional multicast IGMP join. We've got a vision mixer that takes it, or a vision mixer that takes it. We've got a multi-view that takes it. So the really efficient thing here is the camera feed is sent in once and it's replicated by a node in the network and delivered twice. Only delivered to where it's needed to in this particular case. So it fits our workflows very well. Get a lot of questions about layer 2 or layer 3 networks. I just want to cover those briefly as well. So IP has been, audio has been IP for a long, long time now. We've had AES-67, we've got Dante, Ravenna, all those sorts of audio standards been used for ages. They're often used in a layer 2 environment. What does that mean? A layer 2 environment means that traffic doesn't necessarily have to escape from the subnet or the VLAN that it's in, but that VLAN, that subnet, can be stretched across multiple switches. So you can have a multi-switch network, but you can have traffic that's passing across it and going to and from endpoints in the same subnet or the same VLAN. That's a really easy way to build a network. It's very simple in terms of configuration. It works really well for audio. Audio tends to be low bit rates. It doesn't work too bad for compressed, transport streams, for example. Again, where the bit rates are relatively low, you can build a network where you've got a lot of capacity compared to the traffic you're sending. Going layer 2 can make things like control protocols quite simple because they don't have to be routable. They can use locally scoped techniques like multicast DNS, MDNS, for registration discovery, for finding the endpoints. It can make an audio system very simple to make plug and play. In terms of network space, resilience is available through techniques like MLAG, multi-chassis aggregation. So you can provide resilience, you can provide some scale, you can provide a lot of leaves attached to audio devices. For audio, it works very well. Okay, so how about layer 2 for live production, for ST2110, for large bandwidth flows? So unfortunately, layer 2 doesn't scale so well for live production. Live production is, there's a lot of high bandwidths available. Imagine it's a bunch of 2 or 3 gigabits or 9 or 11 gigabit flows, depending what standards you're running in. Let me just describe where the problem comes from. In a multi-switch layer 2 topology for multicast, you end up having one of the switches in that layer 2 domain will act as a querier, and pretty much defined by the way multicast works, by the way the RFCs work. All the traffic that is not in that switch, all the traffic attached to the other switch, the left-hand switch in this drawing, will have to flood towards the querier. It doesn't have a choice. That's the way that multicast works in layer 2 environments. So all those 3 cameras, they're used by the multi-viewer there on the left. But irrespective of whether they're needed on the right, they'll be flooded towards that querier. They're flooded towards the querier so that the querier can understand what traffic is in that multicast layer 2 domain. So we've immediately built a system where we've got these big flows, and we've got to make sure that we've always got enough capacity between layer 2 switches to accommodate all of those flows, however big they happen to be. So we potentially need large pipes between layer 2 switches. Another thing is we've built a big failure domain now. Layer 2 domains are known as broadcast domains or failure domains. So this is exactly the case in point, really. If traffic was to flood unexpectedly, it floods within the VLAN. So this is just expected flooding, and it's going to cause trouble if there's too much of it. So it doesn't really scale very well in terms of the flooding. And if you want to build a larger system with more spine layers, for example, you can only do that with MLAG in this architecture, and you're limited in MLAG to 2 spines. So you've given yourself a bunch of places where this is a bit of limitation. So the right answer is to go for layer 3. Layer 3 means that each of the VLANs is a smaller failure domain. You connect together these VLANs using routing, traditional routing that we use every day in the data center. And you can then either use dynamic multicast, PIM, IGMP to connect together these layer 3 multicast VLANs, or you can use some sort of SDN. We'll cover that one later on. So the big plus is no more failure domains are smaller, and the flooding that was described in the previous drawing towards the query, that doesn't happen anymore. So you've controlled all of that now. And of course, IGMP PIM or a broadcast controller with an SDN capability can configure and control what transits between those devices. So way more controllable. What about network architecture? Now we've understood some of the basics of multicast and layer 2 and layer 3. How do we build this into good 2110 network architectures? So the simplest thing to do is 2 big switches, a red one and a blue one, or an amber one and a blue one, whatever you want to call it. This is like, there's plenty of these around. Quite a lot of the early installations look like this, two big switches, whatever size you need them to be. And there's a lot of scope from a 32 times 100 gig up to 576 times 100 gig, for example, size of switches available from many vendors. What that gives you is incredible scale. If you think of that 32 times 100, that's basically 300 squared UHD. If you think of the 576 squared, that's basically 5,700 squared UHD. So they're incredibly large. 400 gig will bring that up by a factor of, well, 4, strangely. So even bigger. Not the difficulty, but there's a few downsides. Large physical failure domains. If you break a switch, you've broken half of your network. Typically, these guys have less flexibility in connectivity options. 100 gigs, 25 gigs, 10 gigs, all good. 1 gigs. Once you start using 1 gigs, you're starting to burn relatively expensive ports. And of course, it might not be suited to your geographic needs. You may have a campus, you may have distributed production facilities. This might not work, might end up as a central apparatus room that's too far from everywhere. Big plus point, you can run this with IGMP perfectly happily. Very, very simple. You can buy the right non-blocking line rate switch and IGMP will be fine. You don't need any SDN. So very simple option, this one. Hub and spoke. I'm going to cover 3. I'm going to cover big pair of monolithics, hub and spoke and leaf and spine. Hub and spoke is really just a special version of a leaf and spine to me. It's a leaf and spine with just a single spine. Now, I've drawn the red one. Obviously, there'd be another pair. There'd be the blue one to go with this. But this model gives you kind of an answer to that geographic problem. You can move the leaf switches somewhere else. Gives you an answer to the requirement to change the speeds or have flexible I/O, because you can have a 1 gig switch or a 10 gig switch or a 25 gig switch attached as a kind of, not quite aggregation, but a way of changing the speeds of your audio or whatever it happens to be. So this is a great way of going, and it's very simple. You need to really think about whether you're going to consider this to be a non-blocking architecture, in which case you've got a lot of uplinks, or whether you're going to consider whether your workflows need non-blocking, whether you can, each component needs to be non-blocking, but does the network need to be non-blocking? Can you have some sort of orchestration or SDN system that can make use of the bandwidth you've got without having to have 100% capacity? That's a really big question that's worth thinking about at the beginning of the process. The other benefit of this sort of approach is because you've got a central core, you can grow the size. You can start with a core, add things, bolt things onto the core like a vision mixer or the multi-viewers, if that's what you want to do, not if you don't, and then add more leaves as the system gets bigger. But because it's a multi-switch environment, you do need to think about SDN. Have a chat with the right technical people to decide whether that works. Leaf and spine. So this is a traditional data center model, multiple spines, multiple leaves. It's a CLOS network. Very scalable, 3 hops from anywhere to anywhere, easy to accommodate the leaves, smaller failure domains in terms of physical sizes, distributed again. It's all good stuff, but it's quite a complicated network. You are really now going to have to seriously think about a relatively capable SDN controller or orchestrator to make sure that the flows in your network are going in the places you want them to be, and that they're balanced, and that you're not oversubscribing particular links. I'll talk about SDN again later on. Because we're talking about multicast is UDP. There's no TCP protection. If a packet gets lost, it gets lost. It's being sent with best effort. There's no retry. There are some standards include forward error correction, FEC, application layer FEC, to correct any lost packets, but typically 2110 is not sent like that. It's just sent as either single stream or a pair of streams, a -7 diverse stream. if you send the two flows, the red flow and the blue flow from a camera, you can send them through two separate networks, and you can receive them at two receivers on the multi-viewer, for example. And if a packet is lost from one side, it's statistically incredibly likely to still be there on the other side. So cosmic ray strike packet loss can be dealt with fairly easily. A downed link or a broken switch or a switch in maintenance or whatever happens to be, bad optic, those things can all be kind of protected against using -7. The simplest way of doing that is this red-blue air gap network, where red things go to the red network and blue things go to the blue network. Very simple to separate, very simple to give you the diversity that you're looking for. We're starting to see some people build kind of a purple hybrid network or a hybrid purple network. So this is a red and a blue network primarily, but to house some single home devices, less expensive devices, some audio devices, microphones, speakers, monitors, some things like that don't have two physical connectors. So they may even not create two physical streams. So think about whether you need some purple leaves, for example, to sit somewhere in your network and accept connections from those sorts of things to deliver a microphone into both sides of your network. Of course, you can use Multicast to deliver that to two places. You're going to need some sort of mechanism to make sure that you don't end up bridging the two networks and leaking red traffic to the blue network and vice versa. But that's something that good network guys can help you with, or a good SDN system can do. Purple networks, right? We're really now starting to ramp up the complexity. So in a purple network, there could be no defined red or blue leaves or spines. You could just connect things together, put your camera into two leaves, put your multi-viewer into two leaves. They still have red and blue flows, but if you arm yourself with an orchestrator or an SDN controller that understands your network and understands the need for diversity, then potentially you can build a network that looks like this, a converged purple network, where you don't allocate those roles in the network. They're allocated kind of virtually. So here, for example, that particular flow, let's say from the camera through to the multi-viewer, it goes in and it bounces through those two, the red and the blue that I've identified there. But they're not red and blue all the time. They're red and blue for that particular flow. They could be the other way around for a different flow. So it gives you a lot of flexibility in your network. It gives you a lot of choices in the case of failure or maintenance, link failure or switch failure or device failure or maintenance upgrade, whatever. You can think of this as a network which has got 100% resilience with -7. If you take out some of those elements, some of those spine elements, does it still have 100% resilience, or does it have 100% throughput? You get to choose that, really, or your orchestrator or SDN controller gets to choose that. So I've not seen as many of these yet. This requires quite an advanced SDN controller and quite a lot of experience and thought to make sure that the failure modes that might happen in the network can be isolated and ensure that that doesn't ripple through to affect other unaffected at the moment points in the network. So some choices there. In fact, there's lots of choices, and I think that's one of the things that IP brings is a lot of flexibility. So whether you want to build a system that's relatively simple, red and blue, air gapped, monolithic, through to purple kind of leaf and spine, there's a continuum there where you can make your choice based on the things that are important to you. For example, your levels of knowledge, the skills that your broadcast guys and IT guys have got, the sorts of flexibility you're looking for, the risks you're prepared to take. That's kind of a very quick overview of the architectures that are possible. Going to talk a little bit more now about SDN, software-defined networking. What does it mean? When would you use it? What does it do for you? So we've kind of heard that traditional multicast gets delivered using PIM and IGMP. They're the protocols that allow the multicast to be delivered. They're the protocols that allow sources to register their flows and endpoints to request them and have them delivered. So basically, senders send, the camera here is sending, and endpoints that want to receive to do an IGMP request. So we've got a multi-viewer and a vision mixer. It's saying, please, can I have the flow from that camera? Thank you very much. The network is configured in such a way that these flows are delivered dynamically. Replication is provided in the fabric. It's very standards-based. It's very interoperable. Works very well with any routing protocol. PIM is a protocol independent multicast. So you can have any underlay you feel like. It's very simple, but it has some limitations. You know, if it's that good, why would we not just use IGMP everywhere? So it's IGMP and PIM are not aware of a lot of stuff. They're not aware of the link capacity that you've got in your network. They don't know whether the uplinks are 10 gigs or 100 gigs. It's not aware of the size of the source flows. Is it a 1 gig? Is it a 1 gig camera? Is it a 10 gig camera? It doesn't know. It doesn't know that. It doesn't know how to load balance dynamically across multiple bearers between switches or multiple uplinks between multiple spines. It doesn't know how to do that. And it's not aware of the state of the rest of the network. It doesn't know if you've taken, it does know if you've taken a spine down, because that spine will have been removed from the routing tables. It won't be able to access that. What it doesn't know is that having had that removed, it doesn't have enough bandwidth in the rest of the network to deliver the traffic that it was delivering before. So there's something else we need. We need to do something other than just IGMP potentially in a complex network, in a multi-switch network where you're trying to drive towards using as much of the bandwidth as you can. And that thing is some form of SDN, software-defined networking. It's massively nebulous. Most of my colleagues hate the term because it doesn't mean anything, and yet it means everything. So in the truest sense, well, in a sense, software-defined networking is kind of taken to meaning separation of the control plane and the data plane, so that instead of packets being delivered as a result of processing that is done to understand the source IP address and the destination IP addresses, for example, in the case of multicast, and who's asking for them, packets are orchestrated, and the network is told what to do with them. If I see a packet that looks like this, I'm going to do that with it. It's very prescriptive, but it does allow you to take that idea and create external orchestrators or SDN controllers that can be very system aware, high level, make decisions that are much more coherent across a large network, and with an understanding of broadcast workflows and broadcast priorities and the signal flow priorities that you've got in your network. So we move from having a paper map where we can see what the route is, and we can choose a route, we can choose the shortest route, but that's only the shortest route on paper. That doesn't include the roadmap, the traffic jams, the diversions, the fact that the map is out of date. Doesn't include any of those things. So think of SDN as having, Google Maps or a TomTom for your IP routing for your multicast. That's kind of where I think of it. In practice, what it looks like is you tend to have a broadcast controller. It's already got a load of device controllers talking to things. You throw a network controller in underneath that. Architecturally, there's a network controller between the broadcast controller. And the job of that network controller is to understand the broadcast controller's requirement. Please connect A to B, and it's a 3 gig stream. It can take that, and then it'll use its understanding of the network to deliver that 3 gigs safely through the appropriate paths in the physical network. So what we've achieved is we've got some very nice architectural responsibility separation. We've got a network, we've got a network controller, and we've got a broadcast controller. So the broadcast controller continues to do the things it's always done. The network controller abstracts away the bandwidth constraints and the requirements and the diverse paths, if that's what it's doing for you, and essentially delivers to the broadcast controller connectivity that it can understand and trust, and a bunch of telemetry back. The nice thing about that architecture with that network controller is you can you have a choice. You have the option of kind of best of breed type architectures in that section of your network, in that section of your broadcast facility. So, you can separate out, if you want to, the broadcast controller from the network controller, and you can continue to choose the broadcast controller that works for you because you've already got it, or you love it, or it does a specific thing. I know plenty of broadcasters who've got 3 or 4 broadcast controllers because they do different things in different places. That makes perfect sense to me. Then what you want is a network controller, an orchestrator, an SDN that does what you need for you underneath that broadcast controller. And that might be pretty simple. It might be air-gapped red-blue network, or it might be quite complicated. You may be choosing a purple network, so you may need a different kind of class of SDN controller. It may be that you're not too fast. You've got a scheduling system that sits on the top of this, or you might be that you need to closely integrate resource management as part of that network orchestration piece. I don't know, but being able to split them out, I think, gives you a lot of choice, gives you a lot of opportunities to kind of choose best of breed for the layers that you care about. I'm going to now just finish off with a little bit about PTP. Can't talk about 2110 without PTP. So let me just run. This could be another whole entire hour. It's not going to be. We'll just run through some very brief bits. So obviously 2110 relies on PTP. It relies on having the timestamps in the flow, in the essence. They start as PTP timestamps, they become RTP timestamps. But fundamentally what they're doing is they're allowing the flows to be tagged with a temporal marker that enables you to make sure that at the end of the day your production can have good lip sync and possibly more importantly have multi-channel audio that's correctly captured and correctly processed. So stereo remains stereo, you don't get some nasty phasey stuff happening. And PTP has been used for this purpose in audio for a long time, AES67, based on very much the same things as 2110. So typically, you're going to have a couple of GMs for resilience. There's a couple of architectures I'll share with you here. Here I've got a red and a blue air-gap network. It could equally be the other network types if you like, but I'm just showing you a red and a blue leaf and spine pair of networks. So typically my recommendation would be a top-down spine-fed PTP arrangement. Stick a couple of distribution switches above the spines. Use those distribution switches to do the speed change from the GM copper connections through to the spine layer, and use them to do the first kind of BMCA hop where the 2 GMs will fight out who's going to be in charge. That can be, whether that's transparent clock or boundary clock, doesn't really matter. As long as what you install is PTP aware switches with boundary clock or transparent clock, what you're doing is removing the jitter, the unknown timing jitter from the PTP packets. And what that makes is it's a lot easier for the endpoints to regenerate that clock locally with a degree of accuracy that you're looking for. My recommendation would be boundary clock everywhere. It's just simpler. But there are some use cases where transparent has its value. But if you go with the default of boundary, that's good. If you follow this kind of top-down approach, what you've got is a very simple way of delivering PTP. It goes from the GM through the top distribution layer, into the spine layer, and then into the leaf layer. You always know where the PTP is going to be. People worry about how many boundary clock switches can you cascade. We've got 3 here. I would be happy with 5 or 8 or something. So 3 is absolutely fine. You can see a lot of connectivity. What that's giving you is a lot of resilience. Having that little transparent layer at the top is often interesting because it allows you to directly monitor the GM signals themselves. Putting the boundary clock layer in there simplifies the configuration and gives you a different set of monitoring. So you probably have to play with that and see which you prefer, but the simplest, easiest to get going is boundary clocks. And then, so the second architecture I'll share is not my preferred one, but I'm going to share it because there's nothing wrong with it. In this case, we've just flipped it upside down. Still got the GM, still got the distribution, still choose boundary or transparent, prefer boundary, but we're feeding the clock into the leaf layer. Now, If this is a small leaf layer, 3 here, then you could feed every single leaf. If this is an enormous 20 or 30 switch network, you don't want to do that. You'd end up pushing it into just a couple of the leaves or 3 of the leaves, and then the remainder would get fed PGP bounced through the spine. That's why, in that sort of scale, that's why I much prefer this spine-fed, much simpler approach. But ultimately, that's kind of your choice, down to how that suits the way you want to work, really. Can't really talk about PGP without a bit of security. PGP version 2, sorry, has very little, has no security built in. There's a new version in preparation, version 2.1, that does add some security, but that isn't available anywhere yet. And so it's definitely worth having a think about this when you're building a system. I thoroughly recommend the use of the boundary clocks in the leaf layer. What you can do in that case is all of the endpoint facing boundary clocks, you can put them into a thing called PGP role master. What that means is that endpoint, that connection to the endpoint can only ever be leading PGP. I'm going to use the new terminology, leader and follower, leading and following. So the port that is sending PGP to the endpoint can be put into a mode, PGP role master, where that port can only ever be a leader, i.e. it can only ever create PGP. It can't be locked to the endpoint. Why is that important? There's a lot of audio devices out there which need to be able to work in a fairly autonomous way, small number of devices without an expensive GM, and so lots and lots of audio devices can become a GM. They're configured and able to become GMs. So you don't really want that to happen in your network. You want your network to be locked to one of your GMs, the one that you want it to be locked to, the best GM, not to one of your rogue audio devices that's been badly configured, for example. So that role master is incredibly useful in that particular case. So putting that in that layer locks your network against any rogue endpoints. If somebody happened to swap your GM out, that could cause you problems. But you can build in service ACLs, they're called in our world, which would prevent unknown GMs from becoming in charge of the network. So there's not a lot of built-in security, but the network can provide you with some security. And then finally, I wanted to talk a little bit about PGP across a WAN, remote PGP, and cover very quickly when you don't need PGP. So typically, I get this question a lot. I've got 2 facilities, they're attached to a WAN. Do I need a GM in both of them? And the answer really is yes, you really should do. The WAN, you may well know what your WAN is. It may well be an optical network. It may be point-to-point fiber. It may be something with no jitter that you've got complete control over. In that case, that's absolutely fine. PGP doesn't have a problem with latency. It has a problem with jitter. So if your WAN is a low jitter because it's point-to-point optical connections, absolutely fine. Knock yourself out. If your WAN is somebody else's MPLS circuit across a network that you don't have much control over, which is not PGP aware, then that is going to add an awful lot of jitter, which is going to make it very difficult to lock the other end to your GM. So for the sake of simplicity and the sake of not terribly expensive bits of kit in GMs, unless you've got very fine control over that network, I would recommend just installing local GMs. That kind of makes life quite a lot simpler, to be honest. If you've got a good optical network, then maybe have GMs, have a GM at both ends, so you've got kind of resilience and stuff like that. But again, you're kind of opening up your life to a little bit of complication. Where do you need PGP? You don't need PGP in that WAN, for example. If you've got PGP at both ends, you don't need PGP in that WAN, because the only place you need PGP is a place where you have an endpoint which is sampling something, or is trying to use PGP to run its processing rates, for example. So I'm interested in the conversation about whether we need PGP in the cloud, for example. Personally, I'm not convinced yet, but certainly PGP of some sort you're going to need one at each point in your facility if it's across a WAN link. So let me just draw some conclusions then. So choose an architecture for your needs. There are plenty of options. you need to think carefully about your particular use case. That there are no single answers. You have got a unique set of requirements. You will need to decide whether you need an SDN based system or whether you can live with IGMP. That will depend very much on the complexity of your system and the amount of bandwidth you're planning to load up. But again, that is something that you probably need to think about at the beginning of your project and 5 years down the line with your project, because like an SDI router, once you've put an IP router in, what you find is you just plug more stuff into it and you use it more. It adds more value. So you may quickly end up with a bigger system than you're thinking initially. Choose the cloud scale architectures and the cloud scale kind of drivers. Those things will keep you safe. They're best practice. They will ensure that the kit you're buying is designed for scale and reliability and resilience. Use layer 3 where you can. Sometimes you need a bit of layer 2 for audio, but try very hard to limit that. Think about your resilience. Think about how many failures you want to be able to support. Dash 7 will give you a single failure. Do you need to resilient links? Multiple links will give you more failures that you can accommodate. A dynamic SDN type architecture will be able to reroute you around these things. So have a very clear thought about how much resilience you need. Don't let monitoring be an afterthought. I've not talked about it at all, but there's an entire hour's worth of stuff to talk about in terms of monitoring. The SDI system is relatively straightforward. You know where things are. You can unplug a jack field. IP is quite a lot less transparent. It's not at all clear where things may be. And if you unplug a jack field, you've just unplugged, potentially hundreds of flows. So make sure you give your monitoring a lot of thought. And I'd say engage with your vendors early. Make sure you have a chat about what it is you're trying to achieve. There's an awful lot of knowledge out there. You'll need to arm yourself with some, but you don't have to learn it all from scratch. With that, thank you very much.